Yes.
We do have two kinds of systems. One is hardware unit, another is software unit or software system.
Mm-hmm.
All right. What do you mean by hardware unit? Is the physical appearances of any entity is a hardware unit. For example, your mobile phone. All right. The one which you see
Yes.
is a hardware unit. All right.
Hardware unit.
The electric board or the laptop or a computer that you see is a hardware unit, something which you are able to see. All right.
Mm.
And
Yes.
a software unit is basically the coding line, like code programming or clock signals or an pulse generators. All right, something which is virtual, which we cannot actually see. But yeah, what I mean to say is they doesn't exist physically. This is virtual.
Virtual.
All right, so the basic coding, the languages that we have, C, C++, Java, so on and so forth. All right, that's a virtual
Yes.
network. All right.
So it is the link between the software and the
Yes,
hardware.
yes. What is embedded system? A system which is a combination of both software and hardware. All right. So, for example, if you see a fan running, is it a software unit or a hardware unit?
It's a hardware unit.
It's a hardware unit. Simple. All right. And if we say a program or a code or a compiler like Keel IDE software, all
It's
right,
a software.
it's a software, pure software. But if you say a mobile phone, what is a
Mobile
mobile
phone.
phone? Is it a hardware unit
Mobile
or a
phone
software?
is both
Both.
integrated.
That's an embedded system. That's it. Am I clear? A hardware unit which
That's
is made to work using a software system is called an embedded system.
that's
Am I clear?
understandable. Yes. Yes, very clear.
So, for example, a normal watch, like analog watch that we have, is a basic hardware unit. Am I
Mm.
clear? But
Yes.
if we use a smartwatch, like the watch which has sensors in it and which actually measures the number of steps that you make and your heartbeat and all those stuff, right, which has a pedometer, a heart pulse calculator, and your basic module index, BMI calculator, all the stuff in the watch. All right, so
Mm-hmm.
the Apple Watch that I'm speaking about, smartwatch. All
Mm.
right, smartwatch
Smartwatch.
is
Yes.
an embedded system.
That's right.
Am I clear? So what we are actually
Yes.
doing, we are taking up a normal hardware unit and we are trying to write a special set of programming instructions to do certain tasks, and we are going to embed a software program onto a hardware unit, and we are making the hardware unit to perform operations which are required, and then we are
Right.
making that into an embedded system. All
Embedded
right,
system.
so your washing machine nowadays, we say semi-automatic, fully automatic. All right,
Mm.
washing machines. All
Yes.
right, so wherein it is completely an embedded unit, because all that we need to do is program it. Okay, fine. So we need to rinse it for 10 minutes and then wash it for 20 minutes and then spin it for 10 minutes. And we also
Yes.
have programs to select, okay, this much water I want. All right, what exists
Mm.
there? We have a water level sensor, so it detects, we fix a level and it
Level.
detects the water till that level and it stops intake of water. Am I clear? And
Yes.
it will have a timer wherein if I say, okay, I need to wash for 10 minutes or I need to wash for 5 rounds. So for each round it will have a prefix time, and after, say, for example, for each round 5 minutes. So you want to go for 2 rounds of washing. So for each washing it takes what, 10 minutes.
10 minutes.
Alright, after 10 minutes it turns off.
That's right.
Alright, so it's like that. So a hardware unit and its combination with the software technology is nothing but your embedded system.
System.
All right, we
Embedded
understood
system.
it clearly right now.
Yeah.
Yeah.
Just a quick question. The notes that you're using,
Yeah.
Do we get a copy of that just now,
Yes, you
or
get an audio
we?
file that we are both speaking now. As well, you get
Right,
the file that I'm sharing here.
right, great, great.
All right.
Yeah,
So this is what I said. This is a hardware unit, and this is the base C programming. All right. If we
yeah,
transfer the program into the chip, which is a hardware unit, it becomes an embedded system.
embedded system.
All right. So let's basically understand what are the computer hardware units that you might be very well aware of, right?
Yes.
So what are the processors that you know so far?
Oh, in general computer processors, well,
Yes.
Intel, AMD, and they have several from Snapdragon processors to even
Okay, mobile
Motorola,
processor.
yeah, mobile processors, and you have old processors from Zlog,
Okay.
yeah. So there's so many processors out there actually
True, true.
with different,
All right.
yeah,
RAM, random access memory, keyboard, Ethernet card, all these things. This is quite commonly known, and you have used it a lot of times, right? So a
yes,
processor, a memory unit, we call that either RAM or ROM, and with including caches and all those stuff. All
right,
right. And we have an input unit, output unit. All right. And
yeah,
networking units. Networking units like Ethernet card, drivers, your flash card,
right,
and your graphic card
right,
that you insert. All right.
right,
So these are all networking units. And finally, input output like modem, fax.
thanks,
All right. And these are all input output, which could be both used as an input as well as output device.
right.
All right. So this is the basic
So
computer
does the
hardware.
graphic card go on the network yet? Yeah, is it?
Yeah, because that actually uses the network portal.
Right. Okay.
All right.
Right.
So it is about the hardware units that we have. All right. So as I said, embedded system will have a hardware like the processors and all the stuff that we had seen now, and we
Mm-hmm.
also have a application software.
Mm-hmm.
All right, the software that we are going to use, like either C, C++, or Java, whatever program that we
Yeah.
are going to, whatever language that we are going to use in order to initiate the hardware unit. All right,
Right.
so that's the main application software, and there will be some link which actually could link this hardware unit and the software unit, right?
Right.
So that particular link is called RTOS, real-time operating system.
RTOS.
All right.
Yes.
So what is RTOS is very simple. We have a software unit, we have a hardware unit. To link these two, we should have a bridge. All right. So
Bridge.
that particular
Mm-hmm.
bridge, which acts as a link between a hardware unit and a software unit, is RTOS. All right. So
Right.
together is an embedded system. Inside an embedded system, we have a hardware unit, we have a software unit, and the link between those two is RTOS, real-time operating system.
Right. So it is while the program is running. That's what you're saying. Is it under supervision, or
What?
when the program is running the controller, or is it what do you mean when you say the bridge between the controller and the software?
Yes, it is like this. What will be there in RTOS is a compiler debugger. All right, all these units will be there in RTOS, which means all the actions which link the hardware unit with the software technology exist inside the RTOS.
Okay.
All right.
So something like the PC with your IDE or something like that?
Yes, like that. Listen, this is your hardware unit. All right. So here is your
Mm-hmm.
code, and we need to link these two, right? So this is the link if I say. All right.
Right.
And this link is called as RTOS.
RTOS. Uh-huh.
All right. And
Yes.
this entire set is called as,
Embedded system memory.
yes.
Mhm.
Am I clear?
Yes.
Yes.
It says a small-scale embedded system may not need an RTOS. So in some cases, an RTOS may not be required.
Yes, because in few cases, um using merely one compiler can do the task.
Right.
All right. So instead of saying it as an RTOS, we say it as a compiler. That's it.
Okay.
Am I clear?
Got it. Got it. Yes.
So this is the hardware unit, hardware system hardware. How does your embedded system hardware looks like? All right.
Mm-hmm.
So we have a power supply, reset, and oscillator circuit. So we have the main power supply and the clock signal generator. That is oscillator circuit.
All right.
All right. And
Yes, you've
system
described that.
application specific circuit is right here, which means if we want to interface an LED or LCD or any kind as such, will be right here.
Mm-hmm.
All right.
Right.
So power supply and system application
Okay.
specific circuit. And to interface your keypad, mouse, and all the drivers, it is right here.
Uh-huh.
All right.
Okay.
Input devices interfacing, and yeah, output devices interfacing is right here, like your
Mm-hmm.
monitor and all the stuff.
Mm-hmm.
All right. So inside it,
Yep.
we have the core processor.
Yep.
All right. And this is memory unit, program
Mm-hmm.
memory or data memory, whatever. All right. So these are timers is another part. All right,
Okay.
which we're
Uh-huh.
going to discuss in very detail soon. Serial communication ports, wherein the communication between the processors happen using the serial communication ports. I2C bus, all right, UART, RS232,
You
all
are
these
okay.
things are serial
Yeah.
communication ports, which we discuss
That's right.
anyways. All right.
Yep.
Yeah. And finally, interrupt controller, wherein it controls the interrupts. All right, which we are anyways going to see interrupts and the types of interrupts and everything out there.
Mm. Yeah,
Yeah.
that's something I would like to have some good understanding
Yeah,
about
yeah,
both
yeah, sure.
kinds
Each
of.
one of
Yeah.
these we go and discuss in our course, like interrupts
Mm.
one day and then timers, controllers one day, like that. Serial communication ports one day, like that. Clear?
Clear.
Yes. And finally, the ports, parallel ports, like the connectors, we could say.
Right.
All right.
Yep.
So this is the
Parallel
basic
ports. Yep.
hardware unit. So you know the law, Moore's law,
Yep.
like for every 2 years, number of transistors get doubled.
Yes, that's right.
Yes. So a basic example there. Earlier in 1971, Intel started its processor with 2,300 transistors. God damn, now it is 42 million.
uh, can't even keep a track of that. Yeah.
So it's
2,300, it seems to be a reasonable amount to keep track, but 42 million. Yeah. Now it's even more,
yeah,
right?
it's even more. It's close to 65.
Yeah.
Okay. So what are the basic constraints that we have in an embedded system? All right. Embedded system is software designed to keep three basic constraints. All right.
Mm-hmm.
One is availability of system memory, wherein it need to have a specific allocations, because we use it only for system specific applications, right?
Right, yes.
So that's where we tend to use very low level memory chips, right? Instead of extending it to a higher end, we can extend according to the definition or according to the application which we are focusing on. But uh, to be very honest, the memory allocation is going to have a vital role in it. And then processor
Mm-hmm.
speed is also one more constraint that we have here. All right,
Yeah.
and then power dissipation is one more thing that we need to focus on as we are going to develop a application specific embedded unit.
Mm.
There are three things to be kept in mind: memory, processor
Speed
speed, and then power.
and
So
power.
imagine you are purchasing a mobile phone. What are the three things that you look forward for?
These are some of the three things definitely you look for: system
Obviously,
memory,
like what is the memory
speed,
that
and
I can use? What is the speed of the processor, or at least like
mm,
if I say memory, you look for 4 GB RAM or 6 GB RAM, and then
mm,
internal memory of 64 GB or 128 GB, whatever. All right, and what
yep,
is the speed of the processor? Speed of the processor, most commonly in a mobile phone, depends on the RAM that is available, apart from
yep,
the basic allocated RAM. All right, and then power dissipation, like heating up problem. All right, so is it
mm,
overheated or is it low heated, or we need to use heat sinks for that, and how much
mm,
power consumption, how much power it is consuming and how much power it is dissipating. All right, is it
mm,
dissipating more power? Like I have charged it an hour ago and it reached say 60%, and in an hour it lost all the 60%, which means it is dissipating more power, so I need to reduce
more
it.
power.
Right, so
Mm,
any embedded unit, these are the three major constraints, so this is called as a common criteria.
common criteria. Right.
Right.
System memory, speed.
So what is the beauty here is these things: real-time operation, like whatever application that you want to do in day-to-day life, everything could be
Mm,
achieved using embedded unit. It's only a matter of
right.
how you program it.
Mm,
All right, very compact in size, comparatively less cost, we get
mm-hmm.
at a cheaper rate, and time to produce is also less compared to the normal units. It's reliable because it's not a functionality of an electrical unit, because in an electrical unit we cannot actually rely on the results until unless it is very sensitive, but here sensitivity is not a
Mm-hmm.
matter.
Right.
And it is safe because we don't have what we have a very good firewall network.
Mm-hmm.
And secondly, yes, it is safe because it is not going to do any harm as such.
Right.
All right, so energy efficiency is one thing which we need to take care of, and yeah,
Mm-hmm.
security is what we already discussed. So it is like this: user cannot copy the code and then use it again. We're going to give an
Yeah.
end unit to a user. So safety wise, towards the code or towards the mechanical unit could always be replicated. That's what the problem with Oppo and Apple right now running. Right. So they have,
Mm-hmm.
what they have done is they have replicated all the hardware units, but they are unable to replicate the software unit, because software unit is something which cannot be decoded until unless to a maximum extent of security charges that they have.
Yeah.
All right.
Right.
Until unless you're a good debugger.
Yeah.
All right. So it is something that an embedded system offers: a security.
Mm-hmm.
All right, reliability, security, and safety. These three are said to be the most important advantages that we have here. Clear?
Yep.
So we have three kinds of embedded systems. One is small scale, medium scale, and sophisticated embedded systems. All right. So yeah, mobile phone obviously is a sophisticated embedded system.
Mm-hmm.
All right. So what is small scale and medium scale is something which we are going to see now.
Mm-hmm.
Am I clear?
Yes.
Yes. So if it's a small scale embedded system, which means we have a single 8-bit or a 16-bit microcontroller, wherein we have only one controller, like all the project works that students submit in their grade 10, 12, or even in grad. All right. wherein they use only one microcontroller. All right.
Right.
So that's small scale embedded system. Like if you want to flash the LED bulbs, that's a small program,
Mm.
right? So in a
Yep. That's
traffic
a small
signal, we
program.
need to flash the particular red or yellow or green bulb. All
Yeah.
right. So for particular set of time, then what I do is I just take up one particular embedded unit and I program it. So this is small scale,
Gotcha.
wherein
Okay.
I'm using only one microcontroller, that too of 8-bit or 16-bit. All
Mm-hmm.
right. So little hardware and software complexity is very little because after all it's very simple and could be done in a day or two.
Right.
Yeah. It's not needed like if you observe this doesn't require a power supply, clock signal, and all those stuff because it can run even through batteries, DC power. It can even work with DC.
Mm-hmm. Right. Yes.
All right. It doesn't need an AC power. Clear?
Yeah. Clear.
So and software, yeah, as it said, like the hardware complexity doesn't exist. So similarly, software complexity also doesn't exist because it works with simple C programming.
Mm-hmm.
But what is more important is power dissipation. All
Power
right, we need to
dissipation.
use LED, heat sinks. We need to use the relay controllers. All right, and we need to reduce the power that it's going to take when if we are implementing it for long run. Like I
So
said,
this is sort of like, I mean, this is sort of limiting the power decimation when the system is running
yes, yes,
continuously, as in like,
limitation kind of.
depending limitation. Is it sort of like a program within the program itself? If it's been overworked, for example, that could lead to more power dissipation as well, wouldn't it? Like if
No,
the
this is
program is just
not with
made,
respect to the program. It is with respect
the,
to the hardware units that we are going to add on more apart from the
mm,
processor.
right,
Because
processor.
we need to add a heat sink wherein we need to use the ground resistors and all those stuff.
Mm, right.
Clear?
Yeah, clear.
Yeah. If we say medium scale embedded system, so either we can have one single 16-bit or 32-bit microcontroller or a few more, like few here in the sense it's less than two, less than three.
This is 2 or 3 microcontrollers
Yes,
together, as
two
in.
or three, like hardly three. All right,
Mm,
so less than four, I said. It should never reach four, right? So it should be less than four. I said one
less than
or
4.
two or three. If it is one, it has to be a higher end, like 16-bit or 32-bit, and two or three is
Right.
also goes into the same range. Wherein at least one 32 microcontroller or the remaining could be 8-bit or 16-bit or whatever according to the particular application that we are going to uh, make. We're
So,
going to use
so
it.
what you're saying is, like, with the 32-bit microcontrollers, like what ARM offers, they can be considered as medium scale systems?
Yes, it's like this. We can
Mm,
have multiple processors. Am I clear?
mm, yeah.
So if you are using multiple processors and that too 1 to 3, like hardly three different processors, wherein each processor will do a different task. Like for example, your this particular semi-automatic washing machine, I could say, that's a medium-scale embedded system.
Mm, right.
All right, wherein it hardly do what it sets a timer, and it actually asks us for how many rinses that it need to go, and it asks for how
Mm,
many spins that it need to go. That's it.
that's it.
All right,
Okay.
so wherein hardly 2 or 3 tasks, or even if it is 10
Mm,
tasks, if we are using only three microcontrollers, then also we can call that as medium scale.
medium
All
scale.
right, so it's not so sophisticated like a mobile phone.
Mm,
All right, yeah, smartwatch for that sake. All right, even
mm,
a smart watch is nothing but a medium scale embedded system.
medium scale. Okay.
Am I clear?
Yeah, it's not complete. It doesn't facilitate it completely as a phone, but yeah, right,
Yeah.
like a smartphone. Yeah.
and especially the smartwatch, I am saying, which cannot allow a SIM card or a memory card. Remember,
Yeah.
it's a medical. You can call medical watch, wherein it only have the sensors, temperature sensor, heartbeat
Mm-hmm.
sensor. All right, and
Right.
these sensors which exist like pedometer.
Mm-hmm.
Am I clear?
Yep.
And if a
Clear.
smartwatch which has a SIM card in it and a memory card in it, that will be an embedded system, like a
Mm-hmm.
sophisticated embedded system in that case, because that is going to act as a watch as come your mobile phone. Again, it's nothing but the mobile phone.
Yep.
All right. So here, the
Yep.
most
Right.
important, the controllers are either DSP controllers, which is digital signal processing processor controllers, or RISC processors, wherein reduced instruction set for our computers.
Mm-hmm.
So because we are actually intended to use these controllers for a particular application wherein we are going to reduce the instruction set and we are going to reduce the memory allocation of that particular processor. So that's what we mean by RISC
Right.
computers.
Reduce instruction.
All right.
So this is the complete opposite of CISC. Is it the
Yes, it is
CISC?
completely opposite of 6 because 6 is complex wherein we can use it for, it's like an open source. We can use that for
Right.
anything.
Mm-hmm.
Alright, and RISC is opposite wherein we use it for a specific purpose. And that's where we are
Mm-hmm.
reducing the instruction set availability, and that's where we are reducing the memory needed. Alright, so
Right.
we're
Which
going to
consumes
reduce the
memory.
cost of the controller.
Controller. Ah, okay.
Am I clear?
Mm. Yes, clear.
Digital signal processor or digital signal controller is like this for biomedical imaging, for scanning, alright,
Mm.
or ultrasound, alright, or nowadays even X-rays, why not? Alright, for all these biomedical
Mm.
imaging, we use this digital signal processors.
That is it. Yep.
Alright,
Yep.
yeah. So here we have hardware complexity because we need to have lot of subunits, and then
Mm.
the circuit boards of each and every processor need to be taken care of, and each and every processor need to get interconnected in order to bring harmony in the circuit. All right.
Right. Yes.
And
Yes.
similarly,
Understand.
complexity in the programming also exists because your complexity in programming is going to raise up by twofold or threefold depending upon number of processes that we have.
Mm.
All right.
Yep.
So in small scale
Yeah, I can.
embedded system, we don't have an RTOS. As I said, it's basically compiler, debugger, and all those stuff exist.
Mm.
For medium scale onwards, we need an RTOS like a connector, a real-time operating system. That's called OS.
Mm.
Am I
Mm.
clear?
Yep.
So like you have a software OS is Microsoft XP, Windows 7, Windows 8, right? So even here we
Yep.
have an operating system that is real-time operating system, right? Which
Yeah, that's right.
actually interfaces or connects the hardware unit with the software unit.
Software. That's right.
All
Okay.
right?
Debug.
Yeah. Source
Yep.
code
Yep.
engineering tool, simulator, debugger, Keel IDE. Keel is one IDE that we are going to use here.
Right.
Right. So that's about a medium scale embedded system.
Is there any other ID than Keel? I mean, for the 8061 to program,
Yes,
or
there
is it?
are. There are three or four more. Proctar and then what? Monty. These are all the IDs, like integrated development environments that we have. But Kale is most prominent, and then what? It's like global, you can say.
Global. Okay.
Right. It is true for all the controllers, starting from 805 until ARM 7, ARM 9, ARM 11. Till then, Kale works.
Right.
Alright, because Kit
Clear.
has different versions in it, which actually gets updated with respect to the processor that we're going to use.
Right.
Alright. So sophisticated is something which you are all using on hand now. Enormous hardware and software complexity which may need a scalable processor or configurable processor and programmable logical arrays. So we have there we have PLCs, and now we have PLA, programmable logical arrays, wherein which could work with scalable processors and all those stuff. Yeah.
Yeah, yeah.
Yeah.
So this includes FPGAs and things like that,
Yes,
PLAs
yes,
and
yes, true.
oh,
FPGAs, PLCs,
mm,
right? And these are
okay.
not readily available. This is something that we need to develop now by integrating more number of embedded units. All right,
Right.
which involves a lot of processors and all this stuff. All right.
Yeah.
So now, what is a processor? Processor is a heart, like the base of your embedded system. All right.
Yeah.
So it has two things, important units. One is control unit, other is execution unit. Right, something which executes the instruction set,
Control
and the
unit.
next one which controls the instruction set.
Right.
All right.
Fetch. Yeah.
So it fetches the instruction and it executes the instruction. These are the two operations that it do.
Mm.
Clear?
Yeah, clear.
Now let's see what are the various processors that we have. We have general purpose processor, application specific system processor, multi-processor system.
Wonderful.
Am I clear?
Yeah.
So general purpose is microprocessors, microcontrollers, embedded processors, digital signal processors. These are all called as general purpose processors. Application
Right.
specific system processor, which works on a specific application, as I said, RISC processor.
Mm.
All right. We
Right.
call that as application specific system processor, wherein it works for a specific or a defined application.
Define application. Right.
And multi-processor system, wherein we have a multiple processors in a single system,
Yeah.
and each processor doing a different task, and a processor who heads all these processors and then relays the output.
Right. This
All
could be
right,
something like a
master slave
pure
network.
embedded, a master stable. Yeah. Yeah.
All right, a master can have a number of slaves and the output will be defined from the master. Am I clear?
Yeah.
Yeah. So it's a single chip semiconductor device. Microprocessor, I'm not explaining that much. All right.
Yeah.
CPU contains an ALU, arithmetic
ALU.
logic unit, program counter, stack pointer, registers, alright, clock circuit, timer circuit, interrupt circuit. Am I clear? One single chip,
Yeah.
what are the circuits that we have? We'll have ALU on the chip, program counter, stack pointer, registers, clock,
Clock
timer,
register.
interrupt will be there on the chip.
All on the
All on the chip. So what is that we need to add to that particular chip is the memory
RAM
unit,
and
RAM and
memory. Right.
ROM,
ROM.
and memory decoder, oscillator, communication ports, serial and parallel communication
Communication.
ports. Am I clear?
Yeah.
So processor will have what? ALU, program counter, stack pointer, registers, clock, timer, interrupt. We add
Okay.
memory unit, memory decoder, oscillator and communication ports.
Mm.
Clear? Till here?
Yeah. Yeah. Then it becomes a microcontroller basically.
Yeah. So what is microcontroller? If this memory unit exists on the chip,
Mm.
All right. So what we connect is
Yeah.
hardly parallel ports.
Parallel ports.
All right. So then it becomes a microcontroller. So nothing that there is operation wise, there is no difference between a processor and a controller. Both do the same
Mm-hmm.
operation. But in a processor,
Definitely.
we need to connect the memory unit and the clock oscillator, clock signal generator, which is oscillator.
Mm-hmm.
All right. But for in a
Yeah.
controller, it's not necessary because the memory unit and memory decoder with oscillator will be there on the chip.
On the chip.
Am I clear?
Yeah.
Yeah. So how does a general purpose software looks like and application specific processor looks like?
Okay. What does it look
If
like?
you say processor, general purpose software or general purpose processor will have what? These things, a control logic unit, all right,
Mm-hmm.
and then we have a ALU register file, and what we connect is program memory and data memory,
Mm.
all right.
Yeah.
For an application specific processor, your ALU becomes a custom ALU. That's the only difference that you need to observe. Here it's
Right.
general ALU wherein it has all the instruction set, but for an application specific we are going to delete or reduce the instructions that exist in the ALU, wherein it is
Yeah.
going to do only that task. For any other task if you
Right.
input, it's a I cannot do. So error.
What about the program? The program would be different as well, wouldn't it? The execution is going to be different.
Yes, obviously.
Yeah.
Alright.
Yeah.
So then single purpose like fan hardware unit. So for fan, it's a hardware unit. It's not an embedded processor altogether.
Yeah.
Alright. For a fan it only rotates. And for
Mm-hmm.
fan we can have a controller wherein we can implement a control logic. So if you observe we have okay speed 1, speed 2, speed 3, level 1, level 2, level 3.
Yeah.
Alright, we can define the levels of rotation of the motor.
Mm-hmm.
Am I clear?
Yes, clear.
So, but it's not a complete application specific processor, it's a single purpose. What is its purpose? Its purpose is to increase or decrease the speed.
Speed.
Am I clear?
Yeah.
Yeah. So, general purpose processor is a raw material. From there, you design the application specific processor.
Right.
So, we have microprocessor. And do you ever
Mm-hmm.
know that why we call microprocessor as microprocessor?
Because it's just the CPU and we don't have any memory attached to it.
No, I understand what is processor is which don't have a memory
I mean,
allocated, which only do process. I'm asking why it is called microprocessor or microcontroller. What is the importance of micro there?
the micro there.
Yeah.
This is, well, it's not, we're not talking about PC because it's low power, small speed, low speed, application specific, you know.
Do we have something called nano controllers?
No, not, not at the moment.
So why we opted only for micro?
Not really. I have no idea why they call it just
It
micro. I
deals with
thought they may
clock
be
signal. Yeah, don't worry,
clock
it's
signal.
not. It deals with the clock like we give in megahertz, right?
Yeah. Okay.
So we give clock
Yes.
signals in megahertz, the frequency of the clock that we give in megahertz. All right. So the signals that it generate will have a pulse of microns.
Hmm.
All right. It works with micron pulses inside the circuit. So that's why
Oh,
we call
okay,
that as
that's interesting.
microprocessor.
Mm,
All right, chalo, no
that's
issues.
something new.
All right, so single purpose processors, obviously they are fast, low power, small size. Like I said,
Mm,
the application, the small scale embedded system.
small scale and
All
yeah.
right, application specific processor, yeah. So they are a bit flexible, and yeah, cost gets reduced compared to the general purpose processor.
Mm-hmm.
All right, it is actually like this. Instead of using a high end or fully available source, it's like this. Rather than searching from 1,000 entities, search from
Mm-hmm.
100 entities.
Okay.
All right. And what is single purpose is like I'm giving you only this one. Work on that. That's it.
Particular,
Clear?
particular application. Yeah, yeah.
All right. Before going with IC technology, I would rather give you a more specific information about embedded systems. So this is how your embedded system structure looks like. We'll have a sensor, either a temperature sensor or a pressure sensor, whatever you have. All right.
Mm-hmm. Yeah,
And the information that a sensor reads will be sent to an analog to digital converter. All right.
yeah. I like
And
it, yeah.
the converted information is sent back, will be stored in
Mm-hmm.
memory, and will be sent back to the converter again.
Okay.
So the second, this line you see here, this is called as
Feedback line. Okay.
feedback line or feedback loop for this converter. All right.
Mm-hmm.
So this information which is
Okay.
converted will be stored in the memory. All right.
Right.
And it will also be sent to the processor, because processor works only in terms of the digital signal. All right, processor works
It's
in
just
terms of processor works with digital signal. It cannot actually read an analog signal.
right.
All right, so
I'm
that's where
just curious. I'm just curious with the feedback loop. That's a digital signal going back toward an analog path, isn't it? How does that work
no, it will be
exactly
sent to the
with
sensor.
the
Here,
sensor?
it goes
Okay.
like this. It gets stored in the memory. The
Okay.
feedback
Okay.
loop will go and get stored in the memory. All right,
Okay.
this actually shows the path gets repeated for every cycle.
Uh-huh.
Am I clear?
Yeah. Clear.
Yeah. So from memory, it reads the processor can read the information from memory any point of time. Like the input from the sensor could be read from the memory any point of time.
Yeah.
Right. It is just like you save a video from YouTube offline and you can see it anytime.
Yeah.
Yeah. So
True.
just like that.
Mm.
And the processor generates an output digital signal which will be converted to analog by the analog to digital converter, and the output is read from the actuator.
Actually. Yeah.
Clear?
Clear.
Yes. Hello.
Yeah. Hello.
Yeah.
Yeah. It's clear. Clear. Yeah.
So this is something which we had discussed, right? So CPU,
Yeah.
which is arithmetic logic unit, all right,
Mm-hmm.
which don't have all these things: RAM, ROM, input output ports, serial communication ports, timers, all right.
Mm.
So if this entire thing clubbed to one single chip, it's called as controller.
Controller. Yeah.
Yeah. So here we go. This is controller,
Mm.
which has CPU, RAM, ROM, input output, timer. Here, don't get confused. What is CPU? CPU is nothing but ALU.
Earlier. Okay.
All
Yep.
right. So the same. So we think that CPU is our monitor. Sorry, no, our the one which a cabinet, right, which has
Yeah.
motherboard, USB, and all those. But
Yeah.
so
That's
it's not
CPU.
that. Like here, it's ALU basically.
Earlier. Yeah. You're controlling anything.
Yeah.
Fetch and execute part. Yeah.
Yes. True. All right.
Yep.
Now let's quickly go through the basic differences between a processor and a controller. All right.
Yep.
Processor are basically multitasking in nature. So because processor is
Mm-hmm.
a general purpose, it can process anything. All right, it's just like a pipe which could make it flow water or a viscous liquid, anything in that.
Yeah.
All right, it's just a carrier. It's just like a channel which can go with any of the process. All right,
Mm-hmm.
can perform multiple
Yep.
tasks at a time. For example, on computer we can play music while writing text, like multiple operations which are on. All right, you can
Yep.
actually take a photograph. All right, and then at the same point of time you can actually post it on FB, and then same photograph could be taken to the
Mm.
pixel hour, and then you can edit it. All right,
Yep.
multitasking in nature.
Multitasking. Yeah.
Controllers are single task.
Mm.
Right, so they cannot actually pop up multiple outlets at a time
Right.
at the same point of time. I'm checking. It could be used for a number of
Mm.
applications, but at the same point of time we cannot.
Mm-mm-mm.
All right.
Yep.
Yes. So these things externally we need to connect, and they exist internally. All right, the memory
Mm-hmm.
units and
Yep.
input output ports. Clear?
Yeah. Clear.
Okay. So in a processor, designers can decide the number of memory or input output ports needed.
Yeah.
So it exists on the hands of uh, it exists in the
Designer.
hand designer. All right. But in a controller, it's prefixed. Like we cannot actually change it in any context.
Yeah.
All
It's
right.
limited in the. Yeah.
So external support of external memory and input output ports make processor based system heavier and costlier. So because we need to purchase a processor as well, we need to purchase the memory units as well. We also need to purchase the other external units, which means that
Mm.
is going to be a costlier affair for a developer.
That's right.
All
Yep.
right. Therefore, it's going to be a costlier affair for even for the client.
Client. Yeah. And it can
But
take a lot more time as well, I guess.
yeah, for microcontrollers, they are lightweight and cheaper because everything exists
Mm.
on the controller chip itself.
One minute. Yeah.
All right.
Mm-hmm.
Microprocessors will consume lot of space and time,
Mm.
right? Because we need to connect them, program them together, and all the stuff. And it
Yep.
takes time because we need to go for one cycle of debugging, and one cycle of debugging hardware units, one cycle of debugging software units, and all the stuff.
Yeah. Yeah.
But here, it's not needed.
Not
It's one
needed.
go.
Yeah.
It
That's right.
works, works. If it doesn't work, change the controller. Simple.
Mm.
Number of iterations gets reduced, right? Because we have only one chip. If at least any one thing goes wrong, then entire controller is useless, right?
Yeah,
So
true.
change the controller, things done, and then you get the output. But here,
Mm,
it may be a problem in the processor, or it may be a problem in the port, or it may be a problem in the timer circuit. It's like a lot of
mm,
iterations has to happen.
mm.
All right, so there were the testing becomes complex.
Complex. That's right. Yeah, it's understandable.
So we have two architectures here for 8051. The architecture that we have is von Neumann architecture.
Right.
All right, for 8051 microcontroller. All right,
3250. Okay.
and for ARM7 or any other big microcontroller, the architecture is Harvard architecture.
Hard architecture.
All right, two architectures. One is hardware
Two
architecture,
architecture.
other is von Neumann
One human.
architecture. Clear?
Yeah.
Now let's see what is von Neumann. And this von Neumann architecture is because of the scientist called John von Neumann. On his name, this came in. He is the one who
Mm.
started connecting the particular controller like this. All right.
One data pod. Yeah. Yeah.
One data path bus exists for both instruction and data. It is like the same bus is shared between data and
And yeah, for
address.
addressing as well. Yeah, addressing and data
Yes.
and addressing.
As a result, the CPU does one operation at a time. So it is going to be what? Single hop.
Fetching or
Yeah. Either fetch or execute.
execute. Yeah.
All right. So it do only one operation at a time. Clear?
Yep. Yep.
So here you go.
Mm. Function decoding. Yeah.
So this is how the architecture looks like. Program and variable and stack RAM. So variable
Mm.
RAM is the operation specific memory available. Stack RAM is like the program already programmed allocated memory, which is not helpful for us anyways.
Okay.
Which is already programmed, which is not,
Stack RAM.
which has the instruction set, to be very honest.
Okay. Stack. You mean stack RAM?
Yes, which we cannot actually use it.
Oh.
It's not volatile.
Okay.
System
So
reserved.
it's does the user variables and things like in the program, do they get stored in the stack RAM or variable
No,
RAM?
stack RAM has all the instruction sets stored.
Okay.
All right, from
All
static
right.
RAM.
Yes.
All right, stack RAM is
Static
nothing
RAM.
but static RAM.
Mm-hmm.
All right. So if I need to call upon a particular operation, then from static RAM that instruction comes to the variable RAM.
Right.
Right. While it is processing, it goes to program RAM, ROM.
Program RAM.
Am I clear?
So this is variable RAM is sort of like the blank space sort of in
Yes.
between.
All right. So the space which is available for the user.
Mm-hmm.
All right, for conducting the operation.
Operation.
All right.
Okay.
In your mobile phone, if you see, your out of 4 GB RAM that you have, all right,
Yeah.
you'll have one system reserved RAM, like say 1 GB will be taken away by the system.
Yes.
Or
Yes.
we
So
cannot
that's
use all
stack
the
RAM.
4 GB.
Right.
All right,
Okay.
that system reserved RAM is called static RAM.
Static RAM.
All right.
Yep.
Yeah. So we have data, address, and the control. So data either is a two-line bus wherein data could be received as well as sent.
Same.
But address is only
One
stored.
line.
Address is going to be stored in the variable RAM from the memory interface unit.
Right.
All right. So we have instruction decoding and then process.
Process.
All right, happening of the process or occurrence of the process.
Mm-hmm.
Am I clear here?
Yes. Clear.
Now, what is hardware architecture?
Hardware
Hardware architecture
architecture is that.
actually offers a separate storage and single
Mm-hmm.
buses for instruction and data. Wherein it's like this. We have a separate carrier, separate bus for both data and address.
Carrier. I
The
mean, yeah,
basic
data and
address. Right. So for data we have a separate bus, and for instruction set we have a separate bus, wherein both we can actually fetch and execute at the same point of time.
mm,
Am I clear?
clear.
Yes. So by which it's going to happen faster and quicker.
Fast and quicker. Yeah, it
Yeah.
seems.
But again, the
Let's
point
see.
is here, since we are using two address, like here, the data address, all right, it's going to be slightly costlier if we use hardware
More,
architecture.
more
Yes.
routing, as in.
Because we are using separate data bus and address
Mm,
bus. Slightly, like the variation will be what 1 to 2% in cost.
mm,
Am I clear?
yeah, clear.
So that's hardware architecture. That's a basic difference between von Neumann and Harvard architecture.
Architecture.
Right. What are the other differences that we have in von Neumann architecture? All right. So the first difference is they have the shared memory. All right. In von Neumann
Mm-hmm.
and in Harvard, they have separate memories. Am I clear?
For both, yeah,
In
yeah,
one
clear.
human, processor needs to fetch code in separate clock cycle and data in other clock cycle, so it requires two clock cycles to do one single task.
That,
Alright, so
okay.
it is going to take too many clock cycles,
Too many clock cycles. Okay.
which means it is going to consume lot of power.
Mm,
Am I clear? Which means it's going to dissipate more power.
dissipate more power.
Alright, so power consumption is going to be higher, and then it's going to be a the system is going to get heated quickly.
Hit it quickly.
Clear?
Clear.
So what happens here in hardware architecture is like single cycle is sufficient to get the address as well as data, which means number of clock
Yeah,
cycles is reduced by half, which means
half.
power
Yeah,
it's going to consume is going to reduce by half.
that's right.
All right, so which means the power that it's going to dissipate is also going to get reduced by half.
Yeah,
So there's no heating.
no heating.
Clear?
Clear.
And the plus point of one human is it's a high speed and less time consuming, because we have only
Oh,
one memory. So whether we give data or instruction, we go and set only that memory allocation.
right. Okay.
Alright, so it's like this. We have only 10 pages to read. Alright, or 10 pages to search. So you go and read on or search only 10 pages, which is quick and easy. Alright,
Mm-hmm.
instead I have two set of 10 pages. One 10-page book and another 10-page book. Alright, so I have given data. So I need to initially think, okay, fine, I need to go with first 10 page.
Yes.
Alright, and then read 10 pages. Oh no, this is not data 10 page. So I come back to the next 10 page and I read the next 10 page and
Yep.
get the data there.
More time consuming.
Yes. Alright, slower in speed, that's more time consuming. And one human, it is simple because we have only one memory allocation. We allocate it to the data or the instructions. And
Mm.
hardware, it's complex because come on, for each and every time that you need to define two different ports. Alright.
Two different points.
Yeah, two different ports, one port of 60-bit or 8-bit according to the operation, and one port for data, one port for address or
Address.
instructions.
Mm.
Clear?
Clear.
So this is the difference between von Neumann and Harvard architecture.
Mm.
Clear?
Yeah, clear.
So now let's understand what is the difference between CISC and RISC controllers. All right.
Yeah.
Yeah, CISC is a complex instruction set computer. RISC is a reduced instruction set computer, wherein CISC is general purpose, and RISC is for
Mm.
application specific. All right.
Small. Yeah. Applications.
Now let's get into it. CISC, we have larger set of instructions, so easy to program.
Mm. Yeah. Large. Yeah, easy to Yeah. True.
All right. But here we do have very little number of instructions, reduced number of instructions, wherein a programmer should know what are the instructions that are available in that particular controller.
Right. Yeah.
Alright, if he uses a normal code on a RISC controller, obviously that's not going
Mm.
to execute, because there may be few instructions, like for example CLC and CLR.
Mm. 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 Mm.
Alright, so both exist in CISC computer. Even if we say CLC or CLR, alright, that will clear the window.
Mm. Mm. Mm.
Alright, but in RISC processor we are going to remove CLR, because we
Yeah.
don't need to. Am I clear?
Mm. Yeah. Yeah.
So that's
Smaller
where
size.
we need to be very careful. Like the programmer need to be careful here.
So when you're in the risk architecture, I mean, when you have risk sort of programming way, it becomes more sort of difficult to get the application done easier. I mean,
No, it's
or
like it's
difficult to
difficult for the
program.
programmer. For
Mm.
end user, it's going to be cost effective, because we are not using the lot of memory space which have lot of registers and controllers. We are using very minimal number of registers and controllers, right?
Yes.
So it's going to be easier.
Mm.
But for programmer, it will be difficult. Why it is difficult? Because he need to understand what are the instructions that are available and what are the instructions which are
Instruction.
not available in that
Mm.
controller, because it's not common for all the
Not
controllers.
common for all.
It varies from controller to controller.
Mm.
Am I clear?
Yeah. So the programmer has to have some sort of learning curve when he's changing
Yes,
from
yes,
controller to
yes,
controller.
yes.
Yes. Mm.
All right. So the CISC is easier because simple design of compiler considering large set of instructions. But
Mm.
in RISC, compiler itself is a complex design.
Complex design.
Yeah. Many addressing modes causing complex instruction formats. So we have various addressing modes here in CISC, because we have lot
Right.
of instruction sets. All
Yeah.
right. We need lot of addressing space.
Mm.
All right. And here only few addressing modes. So it's like simple.
Right.
All right.
That's
So
an
here instruction length is variable. It varies according to the instruction.
right.
All right. Here it varies. All right.
Right.
So we need higher clocks per second, because
High
we
clocks.
need to set a lot of instructions. All right.
Yeah. A lot of instructions. Higher clocks per second. Yeah.
And it requires less. So CISC,
Low clock speed per second.
yeah,
Interesting.
uh, CISC processor, it has more prominence on the hardware unit. All
Mm.
right. It is prominent when the hardware unit is complex.
Complex.
All right. When the hardware unit is very complex, yeah, then we go with CISC processor, wherein it actually reduces the strain that we take, or it reduces the pain that we take up in programming, because everything is available there.
Mm. Right.
Alright, RISC hardware unit is simple, but
Mm.
complexity in software unit exists.
Mm.
Alright, because this is not general purpose. This is not openly available source code.
Not openly. Yeah.
Alright, and in CISC, control unit implements large instruction set using microprogram unit.
Mm.
So
Mm. Mm.
control
Mm. Mm.
unit
Mm.
task becomes more complex in CISC. Why? The same example that I had said prior. we have 1000 pages book. In that,
Yeah.
you need to search for a word called fetch.
Mm.
All right.
Yeah.
So if you want to uh, check one word called fetch in the 1000 page book, it takes more time.
Yeah.
It's going to
Takes
take
more time.
a lot of effort. All right. But here, it's not like that. We have only one page. In that, we need to search fetch. But
Mm.
we need to know whether the fetch exists in that or not. All right,
Mm.
that's the complexity.
That's the complexity, right?
All right, and it is slower in execution because, as I said, we have a lot of instruction sets. All right, it need to get
Mm.
executed. It need to search and then finally get the code. So it becomes slower. Wherein risk
Mm.
is faster in execution.
Mm.
All right,
Yeah.
pipelining is not possible here. All right, and pipelining is possible in risk because, come on, so two instruction sets which are different could be pipelined together.
Right. Considering in one clock cycle, yeah, within one
Yes,
cycle, so
within
sort of
one
like,
cycle.
mm, mm. Because we were saying two clock cycles for one instruction set,
Yes,
so yeah,
yes,
but
yes, right.
yeah.
Clear?
Mm. Yeah, clear.
So let's understand what is a compiler. All right.
Mm-hmm.
So compiler is a computer program that transforms the source code written in a programming language into a computer language. For
Yes.
example, all right, I wrote a program in C, embedded C or C, normal C language.
Mm-hmm.
Your hardware unit cannot understand C. What it
Yeah.
understands is only zeros and ones.
Zeros and ones.
All right. So a compiler is something which actually converts your C program into a bit of zeros and ones and sends it as a signal to the hardware unit.
That's right. Okay.
Clear? That's a task of a
Yeah,
compiler.
clear. That's clear. Yeah.
What is cross compiler?
It
If
can work on
compiled,
different operating system. Yeah.
yeah, if a compiled program can run on a computer having different CPU or operating system than the computer on which the compiler compiled the program, then the compiler is known as a cross compiler. When are we
Cross
using
compiler.
this cross compiler? Have you worked on program called Linux?
Yes,
Unix,
Linux.
Linux?
Yes, I have.
Yes.
Linux, I have.
Yeah.
Yes.
So the Linux compiler, the compiler that we use in Linux is a cross compiler because what we are doing
Cross
there,
compiler.
we are writing program on a Microsoft
Mm-hmm.
C. We are writing a C program on an operating system called as Microsoft,
Yeah.
and then we are trying to import that program which is in Microsoft OA operating system to a Linux operating system because Linux is also an operating system wherein the program has to
Operating.
execute there.
Yes. Yes.
Right. So there the compiler, the one which converts it, is called as cross compiler.
Cross compiler. That's right.
All
Or
right.
cross platform. Is that another term? Cross platform as well?
Yes.
Cross platform. Yeah.
Which crosses like a cross compiler, which actually converts the program from which exists in a one operating system to a different operating system.
Mm.
All right. Now we have decompiler. What is decompiler? Is the opposite of compiler.
Right.
All right.
Never
It is
have an
that
instance of using it.
what?
With the decompiler, I've never used. I mean, doesn't the compiler include the decompiler or
Obviously, yes. Compiler
depends?
means it compiles and decompiles, but the word that we use for the operation is decompiling. It's
Decompiling.
like coding and decoding.
Right.
All right, we code it, we decode it.
Decoding.
Coding is sending a signal. Decode it is receiving the signal from the channel.
Hardware. Panel or hardware.
Am I clear?
Yes.
So decompiling is nothing but converting the low-level language into a high-level language,
Mm-hmm.
which means from bits to C. Am I clear?
Crystal, yeah, correct.
Yeah, we have a language converter. All right.
Yeah, language
So we
converter.
have Google language, Google translators, and all those stuff in it.
Source to source
All
translation.
right.
Okay.
And what is an assembler?
Oh, so,
An assembler is a program that takes basic computer instructions called as an assembly language and converts them into a pattern of bits that the computer process can use to perform its basic operations. An assembler creates object code by translating assembly instruction mnemonics into opcodes.
mm, 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 mm.
It is like this. Have you ever worked on MATLAB?
Yeah, I have worked on MATLAB.
Yeah, in MATLAB, we have something called as a designing platform. Have you
Mm-hmm.
ever heard of?
Designing platform. No, no, I haven't heard about specifically.
Wherein it's like this: we draw a circuit,
Uh-huh.
in that, and that circuit's output will be generated.
Right.
All right, will be analyzed. Wherein, if you draw a circuit, the hardware unit exists inside that particular circuit you have drawn will get activated, and then the output from that hardware unit will be read and then displayed.
Okay.
Alright, the basic example for this is PSpice.
PSpice. Yeah, okay.
Am I clear? So wherein all that you need to do
Yeah.
is draw a resistor, draw a what a transistor, and then an NPN transistor, make it into ground, and then draw one circuit, basic circuit. Alright,
Mm,
and
mm, mm,
then
mm.
give supply. Give supply in the sense, give the desired supply.
Give
All
the
right.
desired supply.
Then the
Okay.
output gets generated and that will be displayed on the screen. Wherein what is happening here is the port programming or the ports get initiated. All right, using an
Yeah.
assembler, wherein we call that as assembly language.
Assembly language. Yeah. Okay.
All right. So where does assembler works? Whenever we are using assembly language, wherein the ports get initiated. All right. The work of compiler and assembler looks similar,
Yeah, they look a bit similar.
but there is a
It's the
difference.
assembler that.
Yeah,
Yeah.
whenever we are using high level language, we convert that
Mm,
into a low level or a board level language, then it is a compiler's task. But assembler
mm.
gets the ports get initiated. Am I clear?
Yeah. Ports get
When we
initiated.
are using assembly language, what is an assembly language? We have VHDL and HDL. You remember that?
Yeah. Hardware
High
descriptive
definition language or
language.
very high definition language.
Oh
Right?
yes. Yeah, I thought I see.
Yeah. Verilog HDL or whatever, because
Yeah.
three variants: HDL, VHDL, Verilog HDL. These are the three variants that
Very
we have.
well. Mm-hmm.
So whenever we use that programming of VHDL, instead of
Mm-hmm.
compiler, we use an assembler. Simple.
Right. Okay.
Clear? In normal programming,
Big
whenever we work with C, Java, C++, we use compiler.
use compiler. Is it because we are using sort of a low level
High
language
level
and
language to low
then
level, yes.
yeah.
Alright.
Okay.
Whenever we use Linux or Unix, we use cross compiler.
Those compilers.
Alright. And whenever we use VHDL, HDL, Verilog HDL, we use assembler.
Assemblers. That's understandable. Yeah.
Clear?
Yeah, that's great.
Yes. So what are debugging tools in an embedded systems? Alright. So we have simulators and emulators. All right. So
Simulator.
we also have microcontroller starter kits, which we occasionally use.
Yeah.
We most commonly use simulators and emulators for debugging.
Simulator.
All right, you
Debugging.
know what is debugging, right?
Yeah.
So which actually checks or testing ka basic funda.
Yeah. Checking
Check for a
bugs
bug,
in the code.
fix it up.
Mm,
All right.
true.
Yeah. So simulator, what is simulator? Code is tested for the MCU or system by simulating it on the host computer. Used for code development, simulators try to model the behavior of the computer, complete microcontrolling the software. Simulator is like simulate the given circuitry and check for the output, or simulate the entire code and check for the output.
Right. So it does have like a microcontroller sort of a simulator where
Yes,
you
you have
just run the
in
program.
Keel we have simulate and check the output before generating
Yeah.
the output.
Right.
All right, that's simulator. So what are the functions performed by the simulator? Defines a processor processing device family as well as its various versions of target system, wherein it defines the processors, monitors the detailed information of the source code part with labels and system arguments and execution codes in each single step, provides the
Mm-hmm.
status of RAM and simulated ports of the target system for each single chip of execution. It
Okay.
actually monitors system's response and determines the output. Throughput is nothing but output.
Mm.
It actually provides the output contents of program counter versus process registers. It provides the detailed meaning of present command, like what is the command and why is it used and when is it used.
Mm-hmm.
It actually provides monitors the detailed information of the simulator commands as these are entered from the keyboard or selected from the menu.
Right.
There are three conditions. There are three variations in it. Either it can support 8 conditions or 16 conditions or 32 conditions, or there is something called as unconditional breakpoints,
Mm-mm-mm-mm.
which means after 8 conditions it breaks. With each stops or it
Okay.
reiterates. Or 16 or 32 or unconditional goes till infinite.
Mm-mm-mm-mm.
Alright.
Yep.
So this actually supports testing, and it's like breakpoint based testing tool. It facilitates synchronizing and the internal peripherals and delays.
Mm. So that means you can use the computer peripherals for your
Yes, yes.
simulation.
And microcontroller starter kit, as I said, we use it very little time. So hardware board,
Mm-mm.
we call that as evaluation board, and there exists an in-system programmer and some software tools also could be used like compiler, assembler, linker. All right. So
Mm-mm.
sometimes we use IDE software and we limit the code size. All right.
Yep.
But most important thing here is the simulation. Rather compared to simulation, this working with this microcontroller board makes our task look simple, because this looks very real time checking.
Yeah. Real time check-in.
All right, compared to the software version, because in software version what we do is we actually simulate it software and we don't get the feel of real time check.
Right. Yes.
All
We
right.
just set some constant variables and yeah. Yeah. Yeah.
Yes.
Yeah.
Yeah. Now let's look what is emulator. Emulator is a hardware kit or a software program. Like we have two versions. Either it is a we can use a emulator software kit or a hardware unit. All right.
Mm-mm-mm-mm.
So it acts as a different host for the system guest. All right. And what it do is it
Okay.
actually takes out all the input from the system. It's
Right.
just like this. Either it's a hardware unit or a software unit. It depends on what you actually use, because both the versions are available. If it is
Right.
a software version or a hardware version, it gets connected to the system as a guest.
Okay. Yeah.
All right, it gets connected to the system and imports all the information, all the data in the system to it. All right, it
Right.
imports all the data and it executes to check.
Mm-hmm. Check. Yeah.
Actually, instead of simulation, simulation is using the same space, using the same data, using the same memory. All right, but
Mm-hmm.
here we are redefining the memory, we are redefining the entire program.
Mm-hmm.
All right, by which I am not affecting the original space or original data or original memory. Am I
Right.
clear?
Give an example, just an example where sort of emulation, when you say emulator,
What?
well, just give us some sort of example, sort of visual example.
Listen, it is like this. Simulator is like this. You have a system, in that we wrote a program.
Yeah.
What we do, we go
Right.
and simulate the program. If you simulate the program
Right.
for that source code, it displays the output.
Right. Yes,
Right?
that's
If there
understandable.
is a problem in the output, then we need to go and correct the code.
Right.
Alright. Then what we are actually doing is we are using the system memory for that.
System memory. Yes.
Am I clear? So what
Yes,
happens
clear.
is, if there is some problem happened in while simulating, all right, if
You
there is a
can check.
problem while simulating, entire program that you wrote gets lost.
Mm.
You lose all the programming source code.
Right.
All
Okay.
right. Instead of that, what is emulator do? It copies the code to another window. All right, think it like this, though it doesn't happen like that. Instead of
Yeah.
simulating on the same window, what I do, I copied it and pasted on a separate window.
Uh-huh.
All right, and then simulates it.
Okay.
So the originality exists as such. Am I clear? I am not affecting the
Yeah.
original
You know
source.
the affected. Yeah.
Yeah, so I'm just checking the copy of the source code.
Copy of the source code.
Right? It is real time first, and yes, we are not affecting the major main source code.
Mm.
All right, this process is called emulation.
Emulation.
All right, the process of imitating the source code.
Imitating the source code. Yeah.
All right, it imitates the source code. Like, it's like this: we connect this emulator to the system. System reads it as a
Yeah.
test. Then what it do is it copies the content of the system. Am I clear? It acts as a clone.
Yeah. Yeah. Acts as a clone. Yeah, that's
Yeah.
correct. Yeah.
And then in this emulator, the program gets executed. All right.
Yeah.
And then if there is a
And
problem in that particular program, then we go and correct it in the main file.
main file. Yes. Okay.
All right.
That's
So that's about simulator,
emo-
hardware microcontroller unit, and emulator.
emulators.
All right. So
Right.